Hey, Matt and Richard.
Hey, Mike and Richard.
Hello.
Shall we continue the podcasting of the Advent of Code 2024?
Yes,
We shall.
and we should do it now.
And now. Welcome to Hacking the Grepson. All right, we're finally about to wrap up Advent of Code 2024. We are in the home stretch. And once again, Richard is here with us. Thank you for being here. And we're going to just jump right in because we're on day 20, which is called Race Conditions.
I can read the AI summary for this one. A mysterious, massive black building at the CPU hosts regular race condition festivals where programs compete on a winding maze-like track. Each contestant moves in discrete steps, and the race was once predictable until the introduction of a one-time 2 picosecond cheat that lets racers pass through walls. This new twist spices up the competition by allowing strategic wall bypassing moves. I like the commentary from the AI. So basically, you're doing a maze, and you can jump through exactly one wall. Is the TLDR of that already TLDR? The actual problem is
cool.
you're given a map of the track, and you must count all possible single cheats that save a significant amount of time. In the example, we need to figure out how many such cheats would save at least 100 picoseconds. The puzzle's example solution indicates the final answer for that. That part doesn't matter. So cheat and tell us how many times you can do that. I did not solve this one because it's another maze thing, and I just didn't feel like it. But this one seemed relatively straightforward. I had basically two options I thought of upon reading it that I wrote down in my notes for figuring out how to deal with the magically disappearing walls or the cheats, which is either iterate over each wall and rerun the algorithm for each, which would be really expensive but would be fairly simple to do, or weight each wall and limit the weight capacity of my shortest path algorithm to 1. Those are the two things I came up with before not looking at this problem again.
I'm going to guess Richard did the second one. Didn't do any of that.
I'm going to guess he did something smarter.
Not for
You
part
did what?
one.
A third one.
For part two, I did something smart, but for part
What'd you do
one,
for
I
part
did
one?
not. I did your first. For part one, I did your first option, which basically just went and ran the distance calculation, removing one piece of
And
wall
that
at a
actually
time.
was fast enough to complete?
It was horribly slow, but as I was I realized what I should have done while I was running, but I did not finish writing the faster way before it finished running
I've
the
had a
stupid
couple
way.
of those.
That's glorious.
However, I did get to use it for
So
part
let's see,
two.
part two, let's see. First, I'm going to try to guess, and then I can read what you have for part two. You could go through 2 walls.
You're on the right track.
The rules have changed, allowing the cheats to last up to 20 picoseconds rather than just 2. That means you could jump through. Programs can now tunnel through walls for longer as long as they end their cheat on a valid track. This expanded window of cheating opens up even more possible shortcuts. But you still only get 1 cheat. Interesting. With the new, more generous cheating rule, the number of potential shortcuts and time savings greatly increases. You need to determine how many of these cheats would save at least 100 picoseconds. The puzzle provides an example of various... That doesn't matter. Okay, so you can still only cheat once, but you can cheat for longer. That sounds like a pain.
Yes. It wasn't so bad. Like I said, I just needed to realize that I was dumb on part one, and there's assumptions that you can make because the path is only one path. So since there's no actual choices along the path, that means that anywhere along the path has a fixed number of segments before you get to the end. So that means that when you start your cheat, all you need to do is look for which pieces of path you can get to in that amount of time. And if that the length to the end from there is plus the taxi cab distance to that spot is a big time savings. That's all you really need to do. So basically, I went along the path itself, and then for each thing along the path, I checked to see if any of the things within that distance away, the 20 picoseconds, would be farther, would save time, essentially. So the distance to that is a straight taxi cab distance calculation, the X and the Y. And then the time to the end is known because you know exactly how far each valid piece of track is to the end. And so you just add and subtract for each one. So you don't even need to do a solve of how to get to the end.
So you find the shortest path first, and then you're like, okay, I know this one.
Well, there is only one path. So you just find
it's a maze.
the path
it's not,
first.
Right. That's right.
And so
it's because it's a maze, there's only one solution. Now, you're not guaranteed that, but it just happens to be the case. Because I don't think it ever says that.
No. You are guaranteed. If you look at the track, no, it says that that's the whole reason it was boring and they put in the cheats is because there is only one route. So realizing that there's only one route means you don't have to do any pathfinding at all. So everything is cheap. So I just found I found my radius in a really stupid way. I just did an iteration from the minimum radius to the maximum radius, the negative 20 to 20. And then I just eliminated everything that was actually too long for taxi cab distance, found which of those were on the track, and then from there, which of those would actually save time by just doing a subtraction.
Now, did you make sure? So you made sure that you would hit
the
actual track, the actual path that you had taken, right? Because there's dead ends in the maze. I think.
So.
Oh no, there's not. It's literally
there's none.
Wow.
Yeah, that's why it's so boring.
Way easier problem than I thought it was.
It is. That's why. Yeah, that's why you can do that. That's why I realized for part one I was being dumb, because all you have to do is see if your cheat is on a valid piece of track, and if getting to the cheat plus the rest of the time is shorter.
Do I cut out 100 picoseconds, or whatever it is? That's interesting. Yeah, like in their example, there's a very obvious one that I see that would go through 5 walls, which would go from S straight down, and then it's like, bloop, I'm right at the end almost.
Yep.
But I can see a couple of those, actually, because you could also just go straight across there, and that's interesting. That doesn't sound terrible, but I think these problems are a lot of the times a make sure you read them really carefully problem, and this sounds like one of them.
Yeah. After you realize this, this is basically all in the realization of that you can do that. So once you realize you can do that, the problem's pretty trivial. But if you don't realize you can do that, you can waste a ton of time trying to make it fast enough.
Yeah. Interesting. Cool. Shall we look at problem 21?
We shall, and I'm requesting being able to read just because.
Please do. I like that. I almost want to read this one in its entirety, just because this one made me laugh so hard when I was reading it because it kept. Well, I'm curious what the AI had to say about this one. So read that first.
Yeah. This one definitely had a lot of interesting chatter on the subreddit, the Advent of Code subreddit. I remember reading this and being like, "Oh, this seems interesting and fun." And I'm sad that because it was day 21, there was very little, hope that I was ever going to get around to it. But anyway, so day 21 is called Keypad Conundrum, and the AI says, you arrive on Santa's starship and find a locked door that must be opened by typing codes on a numeric keypad. A chain of robots must be used to press the buttons on this keypad. Not you, but the robots. And each robot is controlled by another remote keypad. You must ensure the robots never aim their arms at empty gaps or they will panic. But the problem, according to the AI, is you need to type 5 specific codes on the door's numeric keypad, and each code has a complexity defined by multiplying the code's numeric part by the length of the blah, 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 blah. You're asked to sum the complexity. Okay, so the real meat of this one is that you need to press some numbers on a keypad. Seems easy. Oh, wait, no, you don't do it. You have to program robots to do it.
No, you have to program this robot to do it, but you can't program that robot without programming this other robot. But you can't program that robot without... every time I got to a new...
Matryoshka doll.
And then every time I got to a new one in the when I was reading the problem description. It's like, oh, but there's radiation. Oh, but it's too cold. It's like every time. I enjoyed the problem description.
Yeah,
It
this
seems
one
fun, but I
definitely
didn't
had
have
a
time to
great
work on it.
description.
The initial-
very creative
Yeah.
flavor text for this one.
So there's an initial keypad that's the beginning of it, and then the keypad is pressed by a directional pad, and then the directional pad is pressed by a directional pad, and then the directional pad is pressed by another directional pad, each with various excuses for why they needed another robot in the middle.
What a conundrum.
So, the directional pad moves the robot arm for either the next directional pad or for the number pad, and then there's a little A button, and the A button makes it press the button. So you're controlling a robot that's controlling a robot that then will press the button. And so what they're after is the sequence of buttons that's getting pushed, essentially, from your end to get the correct robot at the.
Did you run into any interesting complications in part one? I didn't have a chance to try part one for this one, but it seemed complicated but straightforward, if that makes sense. I'm like, okay, I see how to do this, but I'm sure there was some sort of performance issues.
It feels pretty follow the instructions, but it's just so many layers of stuff on top of each other.
You would think so.
Oh.
However, I don't know if you saw like our chat for.
I never go into the spoiler things until after I've done the problem.
Each of the keypads, there's multiple ways that you can get from 3 to 7, and you would think that just going left and then up would be the same as going up and then left, but because of the directional pad later, you can get a more optimal solution in some cases if you do one or the other.
Interesting.
Basically, you want to maximize the runs in a particular direction of a particular button, because then you can just press A over and over again.
Sense. Because you don't have to move the arm back to A. Okay,
Right.
so if the optimization piece of it, the actually making it the least number of buttons is the tricky bit of that. Okay.
Yes. So making it the least number of buttons, like, it was really annoying because we would go and we would see that these 3 on the sample are right, but this one's wrong. And now my actual input's wrong. Why? And so for part 1, I ended up going and essentially just finding all optimal solutions for a particular traversal from one button to another, and then essentially trying all those with the next one robot up the chain. And that did get me to the solution for part 1. Eventually, after much annoyance.
Yeah, it seemed like this would be an annoying one. Like I like the idea of it, and it seems fun to implement if I have a lot of free time. But I can also see getting bogged down into off by one errors and other annoying things like that for this kind of problem.
For part 1, that was the kind of error that you run into. For part 2, it was much.
It looks like part 2
much
is
worse.
big numbers. Part 2 of Day 21. A second historian is missing, and once again, you have a chain of robots controlling each other to press the door keypad. This time, however, there are 25 directional keypads controlling each other before reaching the numeric keypad. The same codes need to be typed. So you're basically doing the same thing, but now there's way more intermediate robots, and the complexity of all that just seems to kind of skyrocket. Am I right?
Oh yes, and it's even worse than
You'd
that.
have to.
So
I
you would
assume
think,
memorize certain.
yeah. Let's
I assume
see what you got.
memorize certain pathways that you use to type numbers efficiently, and work backwards from the directions that you need to type on the final keypad, or the numbers you need to type on the final keypad to get there. But with all the extra complexity of the multiple keypads, that I'm not sure that would even approach helping.
Yeah. So approach 1, just try it again. No. Approach 2, try and cache the segments of things that I've already found for each one, and then find the shortest of those and pass the shortest of those cached along to the next one. No. So I did that. The first time I did that, I did it recursively. I'm like, oh yeah, it's way faster now. And then I
ran out of memory, I assume.
Or not segfault, but the recursion is too deep.
I hate when that happens.
You just need more memory, Richard. That's the problem.
Yeah. And then, so I'm like, okay, if I go and look at this, how long will this actual sequence be? Like, rough order of magnitude. Can I even get the actual sequence out? And I calculated how long it would be, and I'm like, that will not fit in my memory.
So you need a new approach.
So can you guess what? Yes. So can you guess what I did?
No.
No.
There's maybe Mike can get this based off of a clue that this has happened before.
Actually, you know what I would do, I think, and I still don't think it would work?
There's a certain animal that you might have that you might want to exclaim.
Go ahead.
Is it aquatic and has a light on its head? I don't know. Oh.
It is. They show up in the funniest of places.
Lanternfish
don't
are
they?
all
Those
over this
lanternfish.
year.
Hate those guys.
Yeah.
Oh,
But it doesn't end there,
not.
of course.
That'd be too easy.
So I went and I essentially mapped the number of transitions from like transformations from one thing
so
to
like
the
one
next.
number to the other, or from one arrow to the other, or something to A. Okay.
Yeah. So, yeah, right. So the transformation of this button press translates to these other button presses for this keypad. Let's count how many more digits there are for that. And that got me fast enough, but not correct. The problem is that for seemingly equivalent button presses, so one is I could no longer, when I went to that method, I had to pick something for the transitions. And so I went and I used what I thought were the optimal transitions that were found in the previous one. Because if you start branching, you're just doomed. So you have to pick some sort of keypad press transition.
You've definitely got a dynamic program.
And I thought that I had...
Okay, what are the small blocks that I'm actually going to store so that you don't have to go down all the branching paths?
Yeah. Right. So you have to pick something. You can't just like say it'll be either up, right, or right, up. So you have to pick one. And I thought that I had the most efficient ones, but I did not. And I ended up going through things that seemed like they were equivalent, and they were actually not equivalent. So almost every single transition that was not just like a straight line transition, I had to go and run it and determine if it was better or worse than before. Let me put in my notes because they look crazy. They look like a madman's notes. Oh. So this is what my notes look like for when I was solving this. They, I would assume, look pretty incomprehensible.
Huh.
These look a lot like the notes that I had for that the problem 15 or whatever it was that I spent.
Yeah. So I ended up just going through, and this is one that I just got a lot wrong because I thought that after my first time I had the optimal one because it was the optimal one for 3 robots or 4 robots or whatever. But it turns out that like you won't uncover all of the edge cases with only 4 robots chained. You need more robots to find out all of the edge cases. And so I basically went and I took each transition from one number to another and tried it out and saw if my complexity was lower or not. And like even with just a regular D-pad, because you think it would be, or not the regular, just the directional pad, you expect it with like the numeric pad because there's lots of stuff where you can transition like from 3 to 7 or A to 7 or whatever, where there's multiple paths, and it makes sense that when you go to the D-pad that it would be better or worse. But no, even with the D-pad, going left and then up from the right arrow is different than going up and then left. And going like any of them, like there was an optimal transition from any of them. And so I just basically worked through all of these until I couldn't find one that was lower and submitted it. And it was luckily correct.
Sounds obnoxious.
It sounds exhausting. Yeah.
It was really horrible. This was by far like the hard. Well, this is by far. I don't know if it's necessarily the hardest, like intellectually, but it was definitely the hardest on
tedious. Like it was just kind of
Yeah.
lots of trial and error until you finally get something.
Yeah. So like, this is one of those ones where little subtleties just keep on building up at every single layer. Like, you can't just do the recursion because it's too slow. You can't just do a blind memorization of the segments because you'll run out of memory. You can't just assume that the direction going up and then left is equivalent to going left and then up. Like all of these things just like stack on top of each other to make you wrong.
Jeez.
Yeah. But eventually, I prevailed.
It does seem like there's at least one of these each year that's like that. Yeah, even for you, Richard. Like there's one that just kind of yeah. Because I remember I don't remember which one it was from last year, but there was definitely like one or two that's just like, you got it, but it was like, but at what cost?
Those are always the ones that end up, if I even get that far, those are always ones that end up pulling me out of the game. I'm like, I'm no longer having fun doing this, so don't do it anymore.
The problem is, like, I always feel
right
like
there.
I'm like 10 minutes away from finishing it. And like 3 hours later,
there was a post. I don't remember if one of you guys shared it with me or if I saw it on Reddit, but it was a cartoon of like, yeah, I'm almost done coding, hon. I'll be right to bed. And it's like 10 hours later. And I was like, and I sent it to my wife, and I was like, this is me during Advent of Code season.
Luckily, there were probably only 2 or 3 this year that took me longer than like a couple of hours or so. But like those 2 or 3 are really pretty brutal.
Yeah. Cool.
Wow.
Anything else on 21?
I think that's the extent of my horrible.
Well, then
notes.
I think we
All
should.
right. Well, then go on to 22.
Yeah, we
I'll
should,
read this one since it's
We should
the
get
first
silly
one
with
I
it.
did in a while. Yeah. So 22 was fun.
Monkeys.
I liked the description in part 1. Spoiler by me limiting it to part 1 on that one. But let's see. So monkey market, not to be confused with the money market. So part 1, story wise, as you arrive in the jungle and a mischievous monkey snatches the historian's device. To get it back, you need a huge supply of bananas, which are their currency. So we once again have
Another
our
currency question.
capitalism in place. And you can only obtain bananas by selling your knowledge of hiding spots on the monkey exchange market. Each buyer on the market picks based on a secret pseudo-random sequence, and if you can predict their numbers, you can time your sales perfectly. So for listeners, pseudo-random is often the way that computers have quote-unquote random numbers, right? It's actually more of it's almost an algorithm to take a previous number and spit out another number and then another number. So if you know that first one, if you know the seed, you can predict what the random numbers are going to be. So this is somewhat similar to that. It's in the same vein. The actual problem was you have a list of initial secret numbers, one for each buyer. Each buyer repeatedly applies a specific 3-step procedure, either multiplying, dividing, XORing, or pruning, which I think was a mod, if I remember correctly, to generate a new secret number from the old one. And you must simulate this process for 2,000 iterations per buyer then sum the 2000th generated secret number across all buyers. I wrote this one. It was fairly straightforward to just follow the instructions and make it work for part one. But it ran slow enough that I knew looking at it that whatever part two was going to be, I would need to improve. Mike, did you try this one?
I did try this one, and I did get part one, and it was definitely
Awesome.
follow the instructions. I ran into one like logic bug of mine that I didn't realize that each time you evolved, which was essentially, get the next pseudo random number in the sequence, that you were supposed to do all three steps. For some reason, I was doing them like in sequence. Like the first time, do the first one, the second
and
time.
then the next time you do that.
As opposed to all
I
three.
also misread it that way.
Oh, you did? Okay. Yeah, I was getting really
I
low
did, but I
numbers.
didn't implement it because I was reading it and I'm like, do I do it that way or do I do all three of them? And then I calculated one number just to see, and it didn't line up with the example. It's like, okay,
Yeah.
let's do this again.
Yeah, but besides that, I have very little code. I just basically have the code to evolve, and then I just run that 2,000 times and add it up for everyone, and that was done. This was yet again another nice one where, like, okay, you read it, you implement the algorithm, and it's done. And then part two is I
still don't understand what part two is, to be perfectly honest.
Yeah,
but before we jump onto
yeah.
that, my class for this, I just made a secret number class, and it adjusted itself. This was another one of those ones where I went down the rabbit hole of trying to figure out Pythonic ways of doing things. And I was like, what if I can extend the int class? And it was just a pain. That is one of those classes that's not super easy to extend. You can do it, but it wasn't as easy as I like. Richard, how did you solve part one?
I just followed the instructions. I made a thing that evolves the number and evolved the number. I made separate functions for each of the steps, even though one is just an OR and another is just a mod. Thing. But I made a function for them anyway.
It's fun to do it that way. Yeah. So part two, my note is literally, I'm not sure I even understand this one. I read it multiple times, and I never quite figured out what they were asking. So I'm very curious when I read this part two AI summary if it will clarify things for me. My assumption was going to be, instead of stopping at 2,000 or whatever it was, keep going until something. And it was that plus some other obscure things. So let's see. Story for part two, buyers' prices are actually just the last digit of each secret number. And these prices fluctuate in a sequence. You have a monkey negotiator. You can't just do it yourself. You have a monkey negotiator as a middleman that will sell your hiding spot only when it sees a predetermined 4-step pattern of changes in price. That was what threw me off. And if the pattern never appears, the monkey simply moves on to the next buyer without selling. So the actual problem says you need to pick one sequence of 4 consecutive price changes that maximizes the total bananas earned across all buyers. For each buyer, the negotiator will wait up to 2,000 price changes for that sequence to appear, then immediately sell at the current price digit. If it does, your goal is to find which sequence yields the highest combined total of bananas. So the actual goal is pretty straightforward here, and they give you a nice upper bound of 2,000. I never quite figured out how to define that sequence, like what that even meant. Still throws me off.
Yeah, that was definitely the hardest part was definitely understanding what on earth they were asking. But basically, since each monkey is producing these numbers and and you want the highest price, but the monkey will only sell on your behalf or buy on your behalf or whatever it is. When you tell them this 4 numbers that it has to remember, and those 4 numbers are the differences in the prices of the banana for the last 4.
So it's 4 deltas. You're saying what the delta is going to be between each number in that sequence.
Yeah, after these deltas,
and it has to be the same for all of the monkeys. Okay.
And it has to be the same. It has to be the same for all of the secret numbers. Yeah.
Permutation wise, you're looking at the only values that can be in there are from -9 to 9 because it's a single digit. Actually, it can only be from 0 to 9, but the deltas can be from -9 to 9, which isn't a huge range, but trying to find, but
Yep.
what is that? It's 20 numbers, 10 numbers? No, it's about 20 numbers. You have 20 times 19 times 18 times 17 combinations of sequences that you'd have to try them all. So I assume there's a smarter way to do this.
Sort of. So what I ended up doing was I did a pre-processing at the beginning where I went through each of the evolutions and I stepped through all 2,000 of the evolutions. As I was stepping through all 2,000 of the evolutions, I built a price map. I built a delta map. I kept track of what all the deltas were. And then I went and I made a delta map. So like the delta map would be what the four numbers are for the most recent deltas. And as I was going through it, the first time a particular set of deltas appeared in the sequence, I would keep track of that, and then I would not keep track of any deltas after it for that sequence. And then so for each
That makes sense.
monkey, I had a map of all the possible deltas that they had.
That makes sense. Okay, so yeah, it's almost backwards from the way my initial approach would have been, which is to calculate all of the permutations of sequences and then try them all. Instead, it's like, well, what sequences do you have? Okay, I'm
Right.
What is shared across the most monkeys with the most values?
Yeah, and then from there, since there's only 20,000 deltas, I just tried them all. And since there's like I don't forget exactly how many monkeys there are, but I got for every delta, I got the price value or the value for each monkey, add them up, and then just took the biggest
Makes
one.
sense.
Bob's your uncle.
Yeah, I think if I could have understood what it was trying to say, for some reason the sequence of deltas wouldn't parse in my head. To be fair, this was something I did like Sunday night or Saturday night after already having a really busy day. I was trying to do like 3 or 4 problems that night in preparation for this podcast. I think my brain didn't work by the time I got to part 2 of 23
There's definitely
or 22.
in every year of
Very
this.
fair.
Now that I've tried actively 4 times, like there are so many examples where it's just trying to read what they're saying and often either overcomplicating it most of the time or sometimes missing like a key crucial detail and spending a lot of time getting the wrong answer until you realize you didn't read this thing quite right. And this is it. Yeah, when I saw the part 2 of this and I saw that the description was about as long as part 1, I was like, oh, this is like almost a completely different problem. Whereas, a lot of times it's like part 1 is the meat of it. And then part 2 is like, yeah, but what about if we make the numbers really big? Or what about if you also have to do this? Whereas this one is like, no.
Or what if there's 3 of you instead of 1?
Right. Yeah.
What if
But
you
this
can
was
time travel? And
Yeah, but this was definitely one where it's like a whole new thing you have to kind of grok before you can even start figuring it out. Regardless of how hard it is, it's just figuring out what they're trying to ask and then implementing it. But also, this seems like the implementation of it was leagues less tedious than the day before with the keypad pressing. Yeah, so...
Oh, yeah. This is vastly easier than the day before. It was relaxing in comparison.
Nice.
all right, day 23. Who wants to read this one?
You're up, Richard. Land party.
Sure.
Oh, I tried this one and I was like, I want to figure this one out because it's about a LAN party, but I never quite got there.
While exploring a secure area at Easter Bunny HQ, you notice posters for a LAN party and download a network map. The map shows which computers are directly connected to each other. You're particularly interested in sets of 3 computers that are all interconnected and whether those sets include a computer whose name starts with T. The problem. You're given a list of connections between pairs of computers. You need to identify all triads of computers, where each one in the triad is connected to the other 2. Then figure out how many of those triads include a computer whose name starts with T.
Right.
I'm actually.
So I did get this one.
I'm actually amazed that the AI used the word triad, and yet that was not in the description.
It's funny because I actually called them that too.
In
my graph class.
The only thing I think I just called them trips, or I'm not sure. I didn't
even give them names apparently.
Yeah, for some reason, like I really wanted to.
Oh, trios! I called them trios.
Trios, yeah. I really wanted to get into this one just because I liked the concept, like the flavor text of it. But for some reason, I could not get from how they were going from the list that they were going, just in the example, the list, and then how they were coming up with the 12 sets of 3 interconnected computers. Like, I actually put some effort into this, and for some reason that was just not computing for me, and it was really annoying because I wanted to go further with this one, but oh well.
Yeah. So let's see. For me, I thought it was going to be pretty straightforward for part 1, but part 2 would probably be super hard. And then it was very straightforward, but I made so many little overcomplications as I was going through it that I had a ton of bugs. Again, this was that same night where I was doing several problems. The biggest unnecessary complication that I added was trying to fully map the entire network.
Of course.
Which was not asked for nor needed. And that was for some reason throwing me off. I don't know why I did it. But yeah, ultimately I had a computer class and a network class. And in my network, I had both a find trios. Oh, no, I just had to find trios. The other thing comes out of part 2. What about you? And that 2 was just like, okay, look at this computer. See who it's connected to. Cool. Is it connected to a third computer that's also connected to to the first one? Cool. That's a trio. Richard, what'd you do for part 1?
So for part 1, I misread it horribly. And so I added, this is a good excuse to add a segmentation feature to my graph library. And so I went and I tried to find all of I added that feature to the graph library of finding all the independent segments. And then I realized, well, why is there just one?
Because everybody's connected.
Then I read it more carefully. Like, there is only one network segment. Everyone through someone is connected.
That was exactly the problem I ran into with my network.
I'm like, maybe I'll need this later. So then I just went and I added finding triads to it, the library, because, hey, why not? Though after part 2, I removed that from the library. Basically, I just took a node and for each other node determined whether the 2 that it's looking at are also connected to itself. And if it is, it's one of the triads. Cool. That's it.
All right, part 2. Richard, you can read this one as well. And then I'll read day 24 since it's my birthday.
So part 2, even after narrowing things down, there are still many triads to sift through. So you decide to find the LAN party another way. You realize that the LAN party must be the largest set of computers where everyone is connected to everyone else. The password is then formed by sorting the names of those computers and joining them together with commas. Oh, more commas. Then the problem. Use the same network map, find the largest group of interconnected computers, the clique, where each computer is directly connected to all others in that group. So then create the password by sorting the computers' names alphabetically and combining them with
So mapping the whole network is useful then.
Turned out to be.
Yeah.
Sort of.
Exactly,
yeah. So I did not solve part 2. I don't remember why. Maybe my notes will tell me. But I did try it. And I wrote, it seemed like it shouldn't be too hard. I was thinking sets and maybe a while loop or recursion would probably get me to where I needed. I did learn a thing about Python during this one, which is actually a very useful thing, which is you can type hint an arbitrary number of items in a set or list or whatever by just using ... That was very useful. I like my type hints. They help me keep things straight in my head.
Okay.
And so in the type hinting, I was like, how do you just say it's a list of some number of things? And I don't care how many.
Yeah, ... normally means that whatever it is going to be defined later. So it's like a pre-declaration.
But in this case, I guess...
I didn't know you could use it for specifying an unknown number of things.
As long as it's... So I list some class, comma, ... And then I get a list of a bunch of those things, which then helped with the
Nice.
whatever they called that, IntelliSense or whatever those hintings are called.
Yeah.
I, again, made a bunch of dumb errors, but I was actually having fun in this one tracking them down because I kept learning a lot of some of the deeper parts of Python that I don't normally touch. I subclassed set, which was a thing that I probably shouldn't have done in retrospect. I didn't end up finishing this one for some reason that I honestly don't recall. My solution seems to be trying. But I don't know if it took too long or what.
Is it still going?
No, I can't.
Even now?
And then I did decide that I should make... I decided I should make a change to my template that I use to generate my each day. To instead of having like a script as my file, have it actually be a class and then subclass certain... I came up with an optimization to my overall flow of Advent of Code. And I think... upon realizing that, I stopped working on any of it because I was like, oh, I should do that. And it was like 2 a.m.
Yeah, this was definitely a very, let's build my library problem.
So what'd you do for it?
So I built my library for this
Always
part.
good.
So I abstracted out a find fully connected segments.
Yeah, I called them find
thing.
chains,
and
but fully connected would have been a much better name.
For every level of fully connected, you know that it's going to be based off of the previous level. So each 2 connected ones are going to be based off of one for themselves. And so that's sort of how I started. Is I found all the pairs of connected. Of fully connected nodes. And then from there, I added those basically all to a queue. And every node decided, am I part of this fully connected set? And if it is part of the fully connected set, it adds a new, it pushes onto the queue a new set with those 3 or n fully connected nodes. And it basically just keeps on going where each node asks itself, is it part of this set until there are no more new sets that are created. And from there, you have not only the largest fully connected set, but all of the fully connected sets.
Nice.
Very cool.
Yeah.
Wow.
That seems, I think, again, the reverse direction from the way I approached it. And I think nine times out of 10 in these problems, if the problem isn't working out, I need to just take a step back and be like, what if I tried the other direction?
Reverse it.
Smart.
Yeah.
Cool.
That's definitely a common theme.
The best day of the year, December 24th. Let's see. Crossed wires. I did actually work on this one and got part 1. You and the historians discover a jungle device that monitors fruit. That's a normal thing to monitor. But it has started producing unreliable results. The device uses a network of Boolean logic gates. They used AND, OR, and XOR, connected by wires that hold initial values of 0 or 1. You record the gate definitions and initial wire states so you can safely simulate the system's output offline. Oh, because you don't want to get shocked. That's right. It had some little arbitrary, you're writing a program because... what do they call that? Lamp shading, where they're just like, let's see. So the actual problem was you must simulate every gate in order to compute the final outputs on the wires that are named with a Z prefix. After collecting all the Z bits into a binary number, you then convert the binary value into a decimal number, and the question is simply what decimal number the system outputs on its Z wires. So for me, this seemed like another good just follow the directions one. So I started with that. The the oh crap clarification moment for this one came in when I realized that we don't necessarily know all of the wire values before starting. So we need to be careful about which ones to execute each instruction or when to execute each instruction. I thought it might be worth working backwards from the Z's and doing what do I need to get this approach, but ultimately what I did is I just kept looping over the list of instructions and executing and removing any that I had enough information to execute. So if I knew the two inputs, then I got the output and I added that to my list of things I knew, and then I would go through the list again. Not efficient at all, but that's what I did. Mike, did you try this one?
I did not. My only note is that it reminded me of a past puzzle, and I found it. I think I may even put it in the Slack at the time. It was last year, day 20, pulse propagation, where you had like flip-flop modules, conjunction modules, and a broadcaster module, and the broadcaster would send a signal out, and you had to follow it and see what do you get if you multiply all the low pulses sent by the total number of high pulses. It really reminded me of that one, and I did put effort into that one and wasn't able to figure out. So I was like, I'm probably it's just once again, like, I mean, I'm doing a lot of listening in these last few puzzles, which is totally normal for Advent of Code because I genuinely don't even like attempt most of these, and I listen to how you guys are solving them, and I sort of follow it sometimes like, you know, like on that chronospatial computer one or of the keypad presses, I'm just like, I don't even know if I would even get anywhere near, you know, even an attempt at a solution. But this was definitely one of those where I'm just like, this is so late in the year. It already reminds me of one that I was not good at. And so I didn't even get, I didn't make any progress on this at all, but I am very curious to find out how you all solved it. So go for it.
So Richard, how'd you solve this one?
So for part one, yeah, I did what you thought about doing and went backward. Basically for finding the last Z node or whatever, and then seeing what it depends on and solving for that and recursively going back. And that worked out fine. I think, Mike, this one's actually considerably easier than the one that you tried last year.
Yeah, my class for this one,
maybe you
my
want
class
to
for this one is
again.
literally, it's called device, and it only has one method in it, which is execute, which is unusual. Usually, I end up with a whole bunch of complications. So this one, like, didn't really need it. I'm just holding the data and doing stuff to it, and the what you're doing to it is very rote, I guess, for lack of a better word. So yeah, I definitely think you would have no trouble with part one.
Okay.
Part two.
Part two.
Well, I didn't finish, but my first note on it was yeesh.
Yikes.
So let's see. According to the artificial intelligence summary, on closer inspection, you realize the device is actually trying to add two binary numbers, one from the X wires and the other from the Y wires, outputting the sum on the Z wires. However, the system is giving the wrong sum for its inputs. Evidence points to 4 pairs of logic gates whose output wires have been swapped. And then the actual problem is you need to figure out which pairs of game outputs have been mistakenly swapped so that the device correctly adds any two binary numbers placed on its X and Y wires. Once the correct pairs are identified, swapping their wires should fix the adder for all inputs. Finally, you must provide the 8 wire names involved in these swaps in a sorted, comma-separated list. The obvious and wrong approach to this one was to find every possible combination of 8 wires that could be swapped and test each case individually. I didn't even try it because I just did the math on it, and it's over 1 million pairs to check just for the sample.
Oh,
and over 2 trillion pairs in the real input. And that was like quick back of the napkin calculations. I was like, nope. I couldn't come up with a more clever way to do it off the top of my head and didn't try. So, Richard, I'm curious what you did for this one.
This is another one that took a while. So it's also one where I'm like, oh, it's a full adder. Let's go and make a visualization. I generally know how one of those would be constructed from gates. Maybe I can just visually inspect it and see what looks amiss. However,
That's a clever approach. I'm like, I built an adder out of logic gates, but it didn't even occur to me to just like visually inspect it.
it ended up looking like that, which is a little bit how an adder looks, but yeah, they added extra unnecessary functionally equivalent nodes.
So I want to say for the listeners
Which
who aren't
was
going to see
annoying.
this picture necessarily, although I think Mike will attach something. My like Rorschach test view of this is it looks like a bunch of cats standing on each other.
It does. Wow. It really
does. Yeah, so I think those are actually some of the valid adder parts then.
Meow.
Yeah, there definitely were things that were unnecessary. Like they always do that in these kind of problems where they'll go off and do some unnecessary calculations and then like divide and then like subtract itself from itself. It's like, okay, I got 0 again. It's like just find where that is and you can eliminate half the problem.
Unfortunately, not quite. This is another one where I was poking at things for a long time, and I'm now not remembering which things I poked at were actually useful and which ones were not. So I did like some sanity checking kinds of stuff, like trying to get all of the parents for a node and seeing, well, okay, so the first thing is we have a full adder. So that means that when we put in bits in these particular registers, we should get different sets of bits lighting up on the output, right? And so the first thing I did was write myself basically a tester for it. So for each pair x, I think they're x and y nodes, I expect a particular z for the output for the if it's for the adding and then the carry. And so for all 4 possible, I think it's 4 iterations of that, I have a test to see if the inputs that I put in match the expected output bits. And from there, I could determine which ones are malfunctioning, essentially. And so I have these tests. And then another thing I did was like I have a get all parents and a get all children. And then from those, I have like a find inconsistencies function. And so you expect that that certain nodes cannot affect certain other nodes, as in there's a direct line between them or not. Like, so you would expect that a not very significant bit could affect a significant bit, but not the other way around. And so we would expect there to be a path from a not significant input to any output that's more significant to it, and we would expect there to not be a path in the opposite direction. And so it found inconsistencies that way. This was sort of useful to me, but ended up not being that useful. I poked at it a long time trying to use methods like that to find exactly which ones to swap, but doing so was making my brain hurt. So I'm like, okay, what are all the pairs of things here? Let's try swapping all potential pairs, because that is computable, while finding all 4 sets is not really computable very easily, but finding the pairs isn't too bad. And so I tried swapping every single pair of things, and then every time I swapped it, I ran my set of tests to see how many errors there still were in the system. So like for this set of bits, are there errors? For the next set of bits, are there errors? For the next set of bits, are there errors? So like each time I swapped it, the number of errors would either go up, down, or stay the same. So after I ran all of those, I found which ones made the number of errors go down. And then from those, I basically manually tried the swap, and if it made it better, I kept it, and then I tried another one because there were more than I think there ended up like being 5 or 6. So I'm like, okay, this is small enough that I can just do it by hand. That had there was like 50 or something that there was like 50 or 100 trials that made it go that improved things, but there are only like 6 or so that improved things by a lot.
And you could only swap a given node or given wire once. Like you couldn't swap, you couldn't
Once,
do A and B
correct,
and
which
then B
helped
and
things.
C. So that does reduce the problem space, which is nice. And it avoids
Yes.
the situation of
Yes.
like, okay, well, I changed A, B, and that made it better, but then B, C made it worse. Or worse, what wouldn't have worked in your algorithms if A, B made it worse. But then once you swapped in B and C, then it would, but since you didn't have that that complication, that makes sense as an approach. I like that.
Yeah, so I just kept anything that made things better and then tried the remaining options, essentially swapping them in. Eventually, I got to no errors detected, though there was one thing that I hadn't tried, and it did turn out after I submitted my answer that I did need the other one because there are there are places in my test where there are 2 things that could work, but there was a test that, while I did test whether the bits were correct for the inputs and outputs for each one, I did not test to see if the outputs for a following on bit got inadvertently also swapped. So it was possible to pass all the tests and still be wrong, and there was one instance where that happened. But after I got that in, after that came the sort of roller coaster, because there was the initial roller coaster where, I have one more option and I submit and and the answer was wrong. But if you look at how you are supposed to submit it, you're supposed to submit the names of the nodes in alphabetical order. And as you recall, I was finding out which nodes these were by hand. And so the first time I submitted it with the incorrect alphabetical order. I did not realize that I had alphabetized it wrong. And so I'm like, oh no, what did I do wrong now?
A comes after B now? Oh no.
And so I'm like, these 2, I think, I forget which letters it was. I think I put it in my notes, but there was 2 letters that I had swapped. My notes say, but wait, N comes before P. I had just alphabetized wrong. I fixed it and submitted again. Okay. Still wrong. I was sad. But I was just about to give up, and I looked at the get list again. Oh, wait. I had sorted wrong again. Z33 is higher than Z17. I submitted it again, and it was correct. So this is why I must have failed as like a GameStop employee, because I could not alphabetize the things on the shelves.
Section Z23 comes after section Z17.
17.
Yeah,
Duh.
come on.
Well, you still got further than I did. All right.
No.
So cool. Final day.
So that's the lesson. Always use the
That's what
computer
computers
to do
are good for.
computer
Yeah,
things
sorting.
for
That is
you.
a very good lesson.
Sorting lists. All right. Well, thank you very much for that detailed explanation. We come to the end of Advent of Code 2025, or 2024, sorry, day 25. And I will read the last one. It only has a part 1 because, spoiler alert,
good.
part 2 of every day 25 is make sure you did all the other ones, and that's how you get your final star. Yeah. But the 49th star is day 25. The chief historian's office is locked, and you discover high-tech virtual 5-pin tumbler locks that must be matched with the correct keys. By converting lock and key schematics into pin heights, you can check each column to see if the pin heights overlap. So basically, I got this one. I did this one. I was surprised. I didn't realize that day 25s were more of a gimme. I just never even tried them in the past. But I got this one, and it seemed pretty simple in terms of like I made a lock class and I made a key class, and I just took the input and converted it to those classes, and then I had the key has a single method called fits lock. So it takes a lock's input and sees if it fits, and then I think you're supposed to. They're asking you,
You were supposed to determine which ones were impossible.
yeah, how many unique lock key pairs fit together without overlapping in any column. So like the key is on the bottom, kind of sticking up, right? And then the lock is in their 2D grid is a bunch of, hash marks pointing down, almost like stalactites versus stalagmites. And so as long as they go together without any of the, on bits overlapping, then they fit, and you just find all of those. So yeah, this one was pretty easy. And then I was so sad to see that I was never going to get that 50th star without doing all the other ones. But yeah, but what I mean, I'm assuming that you all got this and it was pretty easy, but feel free to share.
I actually never had a chance to work on this one, but of them, it was the one I decided would be the easiest that I hadn't had a chance to. Of the ones I didn't work on, this is the one I'm definitely going back to because I'm like, I get part one pretty much immediately. My back of the off the top of my head approach that I wrote down for probably solving this was just counting the number of dots in the lock and pounds in the key for a given column and making sure they were equal. Yep. Because that made sense. And then probably instead of my normal way of storing my grid in Y as the outer list and X as my inner list, swap that just to make my life easier. And I just never had a chance to write it down. Richard, what about you? What'd you end up doing?
So I did not use their suggested method of finding the lengths of everything. All I did was I loaded each possibility into the grid class that I have and looked for places where both of them overlapped. If they didn't have any overlapping areas, then it was a valid key. This was actually one of my favorite day 25s. It was pretty fun. Yeah, then we have part 2.
So, Richard, I think you got part 2. How'd you solve that?
Oh, yeah, this was a tough one.
Yeah. Yeah, so this actually, I didn't get it right away. I didn't get it right away because I submitted part 1 with my submitter, and I did not realize that for part 2, you actually have to click turning in your things. Yeah. And so there was definitely a delay in between my part 1 and part 2 completion. So I did not know that. I did not know you had to actually manually turn your stuff in.
Was the historian in that room?
I don't remember.
Because I love that we went all over the friggin' North Pole and then came back to the original office and it was just locked. And someone's in there. Like, did you try knocking at the beginning of this? Like,
that would be too easy. Then we'd have no challenge. Come on.
Held up the list they've been using this whole time to keep track of where they've been searching. You nod, and the historians quickly work to collect their notes into the final set of pages for the chronicle.
And then mine just says you don't have enough stars to finish the chronicle, though. So that's all the story I get.
it seems like if you manage to unlock the door that the historian is in, that you wouldn't need to get all of the other ones.
Oh wait, I was trying to skim it.
Sure, yeah, we don't want to ruin it for listeners. Earn that 50 stars. Come on, but we'll cheat.
I would never find out otherwise.
Well, at least not yet. I'm just curious. Did you guys think that 2024 was easier or harder than previous years in general?
That's a good question. Individual problems that I found hard were harder than other individual problems from past years. I feel like overall it started a little easier and it ended a little easier, but the middle hump of admin of code felt a lot harder to me this year than in past.
Mm-hmm. Yeah, I sort of agree. The median problem is probably a little bit more difficult, but the hardest problems were definitely easier than previous years. Last year, problem 21, I am still baffled by problem 21 of last year, the one where there's the infinite hiker guy.
Step counter.
Maybe someday I'll understand it.
Well, I think that's how the problem with the monkeys would have been for me this year if you guys hadn't explained, if the AI hadn't explained it so clearly.
The AI did a pretty decent job summarizing those things. I don't know whether that's a good or a bad thing, but It was helpful. Yeah, I mean, I'm just looking at all of the past years that I've done the most on, and I mean, at least for me, it seems pretty similar in difficulty. There's just, it goes up and down. There's just some days that are really hard, and then other days that, like, I don't even know, they might be easy. I just never got to them. But like in terms of the number of stars that I've gotten over the last 4 years, it's about the same. So it's hard to say whether it was easier or harder, except for, like I said, 2015.
I've gotten progressively fewer each year. I got 44 in 2021. I got 40 in 2022. I got 33 last year, and I got 31 this year.
So I got 46 in 2020, 44 in 21, 46 in 22, 45 in 23, and 50
Interesting. We
this
both
year.
got the same number of stars in 2021. And they weren't the same ones. I have a gold star that you didn't have anything on, and you have a gold star that I only have part 1 on. And 24 was apparently very hard that year because nobody has it on our list.
Do you like one of the things I've been doing with Advent of Code is, except for I've used Ruby for 3 of them now, just because that's my most comfortable scripting language. But all the other ones, especially the ones before we were doing it actively, I've tried different languages just to kind of test them out. Are you all? I mean, I know Matt and I tried TypeScript last year together. But other than that, I think you've been doing Python the whole time. What about you, Richard? Are you using this as a playtest for languages, or are you sticking to?
I'm using it as a playtest for my libraries for Python.
That's what it's turned into for me.
Yeah, I mean that seems like a pretty standard way about going about Advent of a Code. Like I'm trying to imagine you not having a library that you build up with like useful classes, like you just writing all that from scratch every year. Like, does anybody really do that, or is everybody doing it like we are?
I did that the first 2 years.
Oh yeah, a lot of people do that every year. In fact, the Kushal who was doing it with us, I think he generally just
Even in the
does it
same
from
language, he
scratch
just
every
rewrites
year.
the same library.
I don't know. I don't know what
'cause if
language.
you read-
he's
Do you
uses.
tend to use third-party libraries, or do you tend to just build everything yourself?
So far, I've built everything myself, aside from last year, day 24, where I used a linear equation solver.
Was that for the snowball one?
And the only reason I used
I remember that one.
Yes, that was that one. And the only reason I used that was because my own one that I had written in college 20-something years ago was being too slow for me.
I have not taken to using third party. I think there was one I wanted to use at one point. One of the like NumPy or one of the like crazy one of the crazy things in Python, and as I was doing, I was like, this isn't what I do this programming contest for. Like I want to write code. I don't want to implement someone else's code. I want to write my own. And that's different from how I write like code for work, because you don't want to reinvent the wheel every time. But for this, I do. So that's one of the reasons I stick with Python is I don't do Python at work anymore, sadly. I like Python. I do TypeScript, and I don't ever write this kind of code in TypeScript, so there's not a whole lot of point anymore.
For me, I definitely use more external tools than you two, but I totally understand why you would want to write them, and the scope of these problems affords you writing them. At least if you know what you're doing and you know what you need to write. Because for me, a lot of the times I just don't even know what I'm supposed to be writing, so I'm just kind of flailing, and I'm not going to flailingly write my own libraries most of the time. But if I did know what I was doing, yeah, I think, especially after a couple years of the same kind of problems cropping up over and over again, the same kind of algorithms, you just want to kind of have your own there so you can tinker with it and not have to use someone else's. But one that I find super useful is, and I've mentioned it multiple times, for doing regex, is like a site like regexer or one of those sites, because it's like a really nice web app that you can type your regex in, and you can see immediately whether it's working, and the groupings, and there's explanations, and there's a reference. Because I just don't do regex most of the time, and so every year I forget how to do anything beyond the most basic regex, and so I find those kinds of tools pretty invaluable.
I always like when we get to the first regex problem of the year.
Which is pretty
'Cause
early,
then
generally.
that's my excuse to go relearn the regex syntax because I can't remember
Yeah.
it.
For libraries, like one of my work responsibilities is basically taking care of the dependency framework for one of the pieces of software and the infrastructure for that. So I have a sort of distaste for dependencies in general and want to try and minimize them almost at all costs. So unless there's a very specific thing that I want to use and have a library for, I try and write it myself.
I think the people who get stuff done really fast and like the top leaderboard, they know all the third-party libraries that are out there and how to tap into them really quickly. Sometimes they don't even seem to write code. They go use like a website that already existed and which is brilliant. Like it wouldn't occur to me to do it that way, but that's also not why I write these. I don't care about winning. I want to write code.
Yeah,
It's fun.
it kind of reminds me of like the speedrunning community in video games. Like
Yes.
there's very different incentives in speedrunning. Obviously, the fastest speedrun wins, and so you're looking for any optimization in any way possible. Although they do tend to separate out fully human versus tasks like tool assisted. Although just as an aside, there's a very exciting thing going on with the original Super Mario Brothers, where someone they're like 0.3 seconds off of what a tool-assisted speedrun of the first Super Mario Brothers is, which is like, unheard of that someone can play the game as well as a computer with perfect inputs can play. So it's possible that at some point, like, you won't even need that separate category because humans are just, can do that so well. I don't know. I just thought that was kind of interesting.
I, meanwhile, have still not beat the original Super Mario Brothers.
What? Well, you can just watch it on YouTube.
Nearly 40 years later? Is that right?
I haven't beaten it
That can't be
recently.
right. No, it is right. Jeez. About 40 years later almost.
Well, eventually Mario does find the princess. Sorry, spoiler alert.
She's not in another castle?
She is in a castle that
She's
you
not
visit
always?
eventually. Yes. Okay, so that's Advent of Code 2024. I said it right that time. All 25 days accounted for. I mean, it was fun. I can't wait to do it again next year, even though my performance is basically the same each year. But at this point, I do it for the podcast because it's awesome to have this discussion about it later. And I learn a lot of things just by listening to how you guys approach these problems that I sometimes look at and it seems impenetrable. But I've also seen someone post like, here's all 50 stars in less than a second. Hit go and it's done. And so, knowing that's possible means that there must be a way for even me to solve some of these problems. And yeah, any final thoughts about this year or coming years?
I always look
fun.
forward to these.
I look forward to the next year.
I wish they were every month and easier
I'm sure there's other,
so that I had time
there's
to do
other
them.
challenges. I just don't think any of them else have.
They're not as good.
They don't have the community. I love
They don't
the
have the
community,
community
around it,
behind them
It
either.
brings the boys to the yard, I think. Okay, well, that does it for this episode of Hacking the Grepson. If you want to listen to more of our discussions about Advent of Code, we have lots of them since we've been doing it for several years in a row, including other ones with Richard. I want to thank Richard yet again for coming on the podcast and sharing your wisdom and knowledge. It was awesome.
Thank you for having me.
Until the next time we talk at you about stuff like this, we now return you to your regularly scheduled lives already in progress.